Okay, so we're going to talk about something called molecular geometry, which is how a molecule actually exists in 3 dimensions. How much space does it take up? Where are atoms in a molecule located in 3 dimensions? So we use this acronym VSEPR. It stands for valence shell electron pair repulsion. And what this does is it tells us the 3D shape of a molecule. So what we had learned about last time in chapter 4 with Lewis structures, they tell us how atoms are connected to each other. In 2 dimensions, but they don't tell us anything about the 3-dimensional shape of the molecule. So Lewis structures are important in determining the 3-dimensional shape. This is the first step in determining the 3-dimensional shape, is having the correct Lewis structure. So it's like we're taking this Lewis structure one step further. So let's define some different terms that we're going to be talking about in this chapter. There's electron pair geometry. Which we're going to abbreviate EG. And then there is molecular geometry. Which is mg, and then there's what's called the steric number. We'll abbreviate that SN. So, electron pair geometry is the shape of the molecule only having to do with the regions of electrons, not differentiating between bonded electrons or lone pairs of electrons. So this tells us the geometry of a molecule not differentiating between a bond and a lone pair of electrons. The molecular geometry gives us the geometry of a molecule. It does differentiate. It does differentiate between a bond and a lone pair of electrons. And then the steric number is just the number of regions of electrons around a central atom. Number of regions, and this does not differentiate. A region can equal a lone pair of electrons or / and a bond. So any bond represents a region. So a single bond, a double bond, and a triple bond, those would all just be one region of electrons. So this is some terminology that you need to be comfortable with as we start talking about molecular geometry. So let's just start with water, for example. This is one that we've done a few times before, looking at the Lewis structure of water. So a question might be, what is the electron pair geometry and molecular geometry of water? H2O, dihydrogen monoxide. Okay, so the first thing that you do when you're asked about molecular geometry or electron pair geometry is you have to draw the correct Lewis structure. So let's do that first. So exactly the same way that we did before, to draw the correct Lewis structure, we need to see the total number of valence electrons for H2O. So H has one valence electron, and I have 2 of them, so that equals 2. Oxygen has 6 valence electrons. 2 plus 6 is 8. So I have 8 valence electrons. So I'm going to put the element with the highest bonding capacity in the middle, which is oxygen. Put oxygen in the middle. I'm going to put a hydrogen on each side. And I'm going to draw a bond from the central atom to the outside atoms. I'm going to see how many valence electrons I used for that bond. Then I'm going to distribute the electrons on the outer atoms first and then come back to the central atom. So I've used 2 4 electrons. Hydrogen has a full outer shell because it only wants 2 electrons, and it's sharing 2 electrons, both of them. So I've used 2 4, so then I would come back here, 6, 8. So that's the correct Lewis structure for water. So this is the first step in determining the correct molecular and electron pair geometry, is writing the correct Lewis structure. Okay, so step 1. Step 2 is going to be determine the steric number. So what is the region, how many regions of electrons around the central atom? Okay, so we said that the steric number is the number of regions of electrons around a central atom. A region is a lone pair and a bond. So this is a region, I'm going to say 1. This is a region, I'm going to say 2. This is a region, 3. This is a region, 4. Bonds and lone pairs both count equally as regions of electrons around that central atom. So the steric number equals 4. All we need is the steric number to determine the electron pair geometry. Electron pair geometry is only dependent on the steric number. So there is a chart in your book. It is table 5.1, and you will be responsible for steric numbers 2, 3, and 4. I'll have to find the 2 and 3. This one just shows 4, 5, and 6, but we have a steric number of 4. Steric number of 4 means that the electron, they call it the electron group geometry, same thing as electron pair geometry. The electron pair geometry for something with a steric number of 4 is tetrahedral. So if steric number equals 4, then that means electron pair geometry is tetrahedral, because that's what it says in the chart. So you're responsible for knowing steric numbers 2, 3, and 4. Okay. So the last thing is the molecular geometry. So the molecular geometry differentiates between the number of lone pairs and the number of bonds. So the molecular geometry is determined by the steric number and the number of regions of lone pairs and bonds. So if we look back at the table, the number of bonded atoms in my example is 2, and the number of lone pairs in my example is 2. So this would have a molecular geometry that is bent. So here, for the molecular geometry, I have a steric number that equals 4. That doesn't tell me everything I need to know. I need to know how many of those 4 regions are lone pairs and how many regions are bonded. So for lone pairs, I have 2, and for bonded, I have 2. So if I look at the chart and see what is the molecular geometry of a molecule that has a steric number of 4, 2 lone pairs of electrons, and 2 bonded pairs of electrons, this has a molecular molecular geometry that's called bent. And what that looks like when you draw it is the molecular geometry, the way that this molecule actually looks, it does not look like this. It looks like this. In 3 dimensions. It's bent. The angle of these bonds is not 180 degrees like it looks here in the Lewis structure. Remember, this Lewis structure just tells us how these elements are attached to each other. It doesn't tell us anything about what it looks like in 3 dimensions. To know what it looks like in 3 dimensions, we need to take into account the steric number, and then for the molecular geometry, how many regions are lone pairs, how many regions are bonded. So this would have a molecular geometry of bent. Okay.